Since the final weeks of July, the entire astronomical community, and much of the world beyond it, has been transfixed by a single point of light racing through our solar system at incomprehensible velocity. 3I, Atlas, only the third confirmed interstellar object ever detected entering our cosmic neighborhood, has captivated scientists and skywatchers alike with its enigmatic behavior and peculiar characteristics. But as October arrived, bringing with it what should have been the most spectacular and scientifically valuable phase of this visitor's journey, something frustrating happened. Just as 3I, Atlas, began its closest approach to our star, growing bright enough and near enough for detailed study with our most powerful ground-based instruments, our view was suddenly and completely blocked by the very object the comet was approaching our sun itself. The vast network of ground-based telescopes that had been meticulously tracking every subtle change in this interstellar wanderer for months found themselves suddenly and utterly blinded at precisely the most critical moment. We had only just begun to unravel some of its mysteries. The bizarre molecular ratios that didn't quite match anything we'd seen before, the dramatic color transformations that occurred not once but twice as it approached, and perhaps most intriguingly, the presence of what appeared to be a strange, anomalous tail extending in the sunward direction, a feature that some researchers boldly suggested might potentially indicate some form of artificial propulsion system rather than natural cometary behavior. Meanwhile, as 3I, Atlas plunged deeper into the inner solar system, subjected to increasingly intense solar radiation, and traveling at the staggering velocity of 68 kilometers per second, fast enough to cross the entire United States in less than a minute, serious questions emerged about whether this fragile visitor would even survive its harrowing journey around our star. The structural integrity of any comet facing such extreme conditions is always uncertain, but for an object whose composition and internal structure remained largely unknown to us, the uncertainty was even greater. But all hope was not lost. While Earth-based observatories found themselves temporarily sidelined by our planet's unfortunate orbital position, we had already positioned a sophisticated fleet of space-based probes, orbital telescopes, and even rovers on the surface of Mars, all perfectly situated to maintain their vigilant watch over 3I, Atlas, as it made its dramatic dive toward perihelion, that point of closest approach to the sun where temperatures soar and cometary activity reaches its violent peak. Would this interstellar traveler successfully navigate the inferno and emerge intact on the other side? Would it catastrophically disintegrate under the sun's searing heat and intense tidal forces? Or would it perhaps do something else entirely, something completely unexpected that would force us to reconsider everything we thought we understood about objects from beyond our solar system? I'm Alex McColgan, and you're watching Astrum. Join me today as we carefully dissect and analyze the stunning new observational data captured during 3I, Atlas's close approach to Mars, discover exactly what transpired during those mysterious weeks when the comet disappeared behind our sun, and examine what some are calling the smoking gun evidence from a powerful South African radio telescope array, evidence that could potentially settle the increasingly heated debate about whether we are observing a perfectly natural, volatile-rich comet or something that might be intelligently and deliberately navigating through the darkness of interstellar space. Even before 3I, Atlas vanished completely behind the sun's overwhelming glare. It had already begun giving us clear and unmistakable warnings that this was no ordinary member of the cometary family. During the latter weeks of August and throughout September, NASA deployed their Swift Observatory, a spacecraft originally designed and optimized for detecting the brief, intense flashes of gamma-ray bursts from across the universe, to carefully monitor 3I, Atlas, as it continued its relentless approach toward the inner solar system. While Swift's primary mission involves hunting for these explosive cosmic events, its sophisticated ultraviolet imaging capabilities allow it to perceive and measure phenomena completely invisible to human eyes. In this particular case, the distinctive glow emitted by hydroxyl radicals, chemical fragments denoted as OH. These hydroxyl molecules represent the broken remnants of water molecules that have been violently torn apart by the intense ultraviolet radiation streaming from the sunday, and what Swift's sensitive instruments detected was nothing short of extraordinary. A massive, sustained surge in the production and emission of these hydroxyl radicals. At a distance of approximately 2.9 astronomical units, nearly 3 times farther from the Sun than Earth's orbit, where one might expect conditions to remain relatively stable and frozen 3I, Atlas was actively venting water vapor at the truly remarkable rate of 40 kilograms every single second. To provide some earthly perspective on this astonishing figure, imagine a fire hose operating at absolute maximum pressure and flow rate, with water blasting from its nozzle in a continuous, violent stream. That's essentially the rate at which this comet was releasing water into space. Except we're talking about a process occurring in the frigid vacuum of space, at a distance where temperatures should theoretically be far too cold for such aggressive activity. For any comet situated this far from the Sun, where ambient temperatures hover well below the freezing point and solar heating should be relatively minimal, this level of water production was genuinely shocking to planetary scientists who had been studying comets for decades. Standard theoretical models and observational data from hundreds of previously studied comets clearly suggest that water ice shouldn't undergo such aggressive sublimation, the direct transformation from solid ice to gas without passing through a liquid phase until the comet ventures much closer to the Sun, typically inside the orbit of Mars, or even closer. The fact that 3I, Atlas, was exhibiting this fire hose behavior so far out strongly hinted that something unusual was happening beneath its surface. This extraordinary activity suggested that 3I, Atlas, wasn't simply sublimating water from its surface in the typical manner we observe in most comets. Instead, the data indicated that the comet was likely violently ejecting entire icy grains and chunks from somewhere within its interior, hurling them outward into the surrounding coma, that diffuse cloud of gas and dust that surrounds a comet's solid nucleus. These ejected icy particles would then find themselves exposed to direct sunlight, causing them to melt and sublimate independently in space, vastly multiplying the effective surface area available for water ice to transform into vapor. This mechanism could explain the unexpectedly high production rates observed at such great distances from the Sunday. But before scientists could conduct the follow-up observations needed to investigate this puzzling behavior further and develop more refined models of what might be occurring within 3I, Atlas's interior structure, the comet executed its inevitable plunge behind the Sun and disappeared completely from Earth's view. Throughout the entire month of October 2025, every single ground-based telescope on Earth, from modest backyard instruments to the most powerful observatory facilities on mountain peaks, had no choice but to cease their observations of 3I, Atlas, as it slipped behind the overwhelming brilliance of our star. This represented quite possibly the worst imaginable scenario for astronomers who had been planning their observational campaigns for months. The most exciting, dynamic, and scientifically valuable phase of the comet's entire journey through our solar system was unfolding on the opposite side of the Sun from Earth's vantage point. This was the period when, warmed by the Sun's intense radiation to temperatures far higher than anything the comet had experienced in potentially billions of years of interstellar wandering, 3I, Atlas would reach its maximum brightness and begin outgassing with explosive violence, potentially revealing crucial information about its composition, structure, and origins. But while Earth found itself temporarily blind to these spectacular events, humanity's remarkable foresight in establishing a presence throughout the solar system meant we weren't entirely without eyes on our mysterious visitor. We already maintain an impressive fleet of sophisticated probes, orbital observatories, and robotic explorers scattered throughout the deeper reaches of our solar system. And as fate would have it, several of these far-flung mechanical sentinels found themselves perfectly positioned to witness the entire show as the comet executed its closest approach to the Sunday. A comprehensive new study, led by Dr. Chi-Cheng Zhang from the prestigious Lowell Observatory in Arizona and Dr. Carl Battams from the U.S. Naval Research Laboratory, successfully aggregated and analyzed observational data collected from 3 specific spacecraft that became our primary eyes during this critical period. Stereo A, which stands for Solar Terrestrial Relations Observatory A, SOHO, the Solar and Heliospheric Observatory, and the newly launched GOES-19 satellite, part of our Geostationary Operational Environmental Satellite System. These 3 sophisticated spacecraft all employ specialized instruments called coronagraphs devices, specifically designed to artificially block out the blindingly bright disk of the Sun itself essentially creating an artificial eclipse that allows the instruments to observe the much dimmer corona and any objects passing through the inner solar system near the Sunday. Under normal operational circumstances, these spacecraft spend their time hunting for coronal mass ejections and monitoring solar storm activity that could potentially affect Earth's satellite infrastructure and power grids. But throughout October 2025, they were hunting something entirely different, an interstellar comet. And what they captured in their data was nothing short of a complete metamorphosis. For months preceding this critical period, as 3I, Atlas steadily approached the inner solar system from the outer reaches beyond Neptune's orbit, its brightness had been gradually but consistently increasing in a manner that planetary scientists could track and measure with precision. Astronomers quantify and describe the rate at which an object's brightness increases as it approaches the Sun using a mathematical power law based on the object's distance from the Sun, typically denoted using the variable r to represent that solar distance. Before October arrived, careful photometric measurements indicated that 3I, Atlas's brightness, was increasing at a rate proportional to r raised to the power of -3.8, a value written mathematically as r -3.8. This might sound like meaningless astronomical jargon, but this figure actually represented a quite respectable and fairly typical rate for an active comet, indicating steady sublimation of volatile materials from its nucleus as solar heating gradually increased. It suggested normal cometary behavior consistent with a dirty snowball model of cometary composition. However, something remarkable and unprecedented occurred once 3I, Atlas, crossed inside the threshold of 2 astronomical units from the Sun, roughly twice Earth's distance from our star. Inside this boundary, the brightness slope didn't just steepen gradually. As models predicted, it went nearly vertical in an almost explosive surge of activity. The new data collected by the solar observatories revealed a brightness scaling coefficient of approximately r to the power of -7.5, a dramatic and frankly shocking increase from the previously measured value. To put this in perspective, this means the comet was brightening at nearly double the rate as it had been just weeks earlier, suggesting a fundamental change in the physical processes occurring on and within the comet. That represents an absolutely enormous increase in activity level, far exceeding what standard cometary models predict for even the most active known comets in our solar system. The comet was clearly shedding mass, releasing gases, and ejecting dust particles at a rate that thoroughly defied the standard theoretical models developed over decades of studying simple, dirty snowball comets. This wasn't just more active than expected. It was behaving in ways that challenged our fundamental understanding of how comets should respond to solar heating. The surge was so dramatic, and the resulting brightness so intense, that by the time 3I Atlas finally emerged from behind the Sun and became visible once again from Earth's vantage point, even amateur astronomers, equipped with modest backyard telescopes and relatively simple camera equipment, were successfully able to capture detailed images of it from their own observing locations. This democratization of observation represented a remarkable moment. Professional observatories with billion-dollar budgets and hobbyists in their backyards were all witnessing the same extraordinary spectacle. Here we can examine some of the most impressive images captured of 3I, Atlas, during this remarkable period of peak activity. In these photographs, you can clearly discern a brilliant, glowing coma, that diffuse envelope of gas and dust streaming dramatically outward behind the comet's trajectory, creating a luminous trail across the starfield. However, the actual solid nucleus of 3I, Atlas itself, that rocky icy core at the very center of all this activity, proves considerably more difficult to make out clearly in these images, remaining somewhat obscured within the overwhelming brightness of the surrounding material being continuously ejected. These particular images were captured by astrophotographer Paul Craggs, who utilized a Dwarf 3 Smart Telescope manufactured by Dwarf Lab, a compact but sophisticated piece of imaging equipment that I've been personally experimenting with and testing myself recently, as the company has graciously sponsored this video to help support the channel's continued production of quality content about space exploration and astronomy. I must say, I've been genuinely impressed with this telescope's capabilities. It's remarkably proficient at exactly this type of challenging deep sky imaging where you're trying to capture faint, diffuse objects against the background of space. The Dwarf 3's live stacking feature, which automatically combines multiple exposures in real time to build up signal and reduce noise, enables it to construct clear and remarkably detailed images of deep sky objects in just a matter of minutes, which is especially impressive considering this is such a compact, portable, smart telescope, rather than a massive observatory instrument requiring extensive setup. Setting up the Dwarf 3 proved remarkably straightforward and user-friendly. Once I mounted it securely on its included tripod stand, the telescope's sophisticated internal systems quickly oriented itself autonomously using star patterns in the sky, making it refreshingly simple for me to point it accurately at whichever stars, nebulae, galaxies, or comets I wanted to image without spending hours on manual alignment procedures that plague traditional telescope setups. I particularly appreciated the telescope's excellent portability, as I certainly didn't relish the prospect of lugging around a heavy, cumbersome traditional telescope setup on cold winter nights when temperatures drop well below freezing and every extra pound of equipment feels like 10 pounds. But the Dwarf 3 is sufficiently light and compact enough to transport easily that I didn't have to worry about that concern at all. I could simply grab it and head out to dark sky locations without requiring a vehicle or significant physical effort. Although the optimal window for imaging 3I, Atlas at peak brightness, has unfortunately already passed as the comet continues moving away from both the Sun and Earth. If you're actively looking for an excellent value smart telescope to help you capture images of other beautiful cosmic phenomena from glowing nebulae where new stars are being born, to dense globular star clusters containing hundreds of thousands of ancient suns, to any future comets that might come wandering past our neighborhood, then I would genuinely recommend giving this one serious consideration. Simply scan the QR code appearing on your screen right now, or use the link provided in the video description below. Then enter my exclusive code ASTROM5 at checkout to receive 5% off your purchase. Now, returning to our interstellar visitor, the most scientifically revealing and telling detail about this newly brightened comet turned out to be something observers had been tracking for months: its color, or more precisely, the dramatic changes in color that 3I, Atlas, underwent as it approached perihelion. For many months during the early observation period, ground-based observers consistently reported seeing 3I, Atlas, displaying a distinctly reddish hue, a coloration quite typical of dusty, organic, compound-rich surfaces similar to what we observed on Oumuamua, that first confirmed interstellar object detected back in 2017 that sparked so much scientific debate and public fascination. Then, as I discussed and detailed in my previous video covering the early observations of this comet, 3I, Atlas underwent its first color transformation and turned a striking green color as viewed by observers here on Earth, a shift that indicated changes in the types of molecules being released into the coma as solar heating increased and penetrated deeper into the comet's structure. Green coloration in comets typically indicates the presence of diatomic carbon molecules, often called C2, along with cyanogen compounds, both produced when organic materials in the comet are broken down by solar ultraviolet radiation. But the fleet of solar observatories stationed in space to monitor our star detected something quite different from what ground-based observers were reporting, a discrepancy that would prove crucial to understanding what was actually happening to the comet through the specialized filters employed by the LASCO coronagraph aboard SOHO and the Secor 1 coronagraph on Stereo A. Zhang and Badams reported in their published analysis that 3I, Atlas, appeared distinctly blue in color relative to the Sun's own spectrum, a dramatically different hue from the red and green colors being reported by Earth-based observers. This blue coloration observed in a cometary coma represents the unmistakable spectroscopic signature of specific gas emissions, primarily fluorescence from carbon monoxide molecules, denoted chemically as CO, and amide radicals carrying the chemical formula NH2. The detection of these particular molecules, glowing in the blue portion of the spectrum, told scientists something profound about what was happening within the comet's interior, as it experienced the most intense solar heating of its entire journey. The interpretation of this color shift suggests a compelling narrative. As 3I, Atlas plunged inexorably toward its closest approach to the Sun, experiencing temperatures potentially reaching hundreds of degrees on its sunward-facing surface, it progressively shed its dusty, reddish, outer protective layer, that ancient crust that it shielded its interior for potentially billions of years of wandering through interstellar space. The increasingly intense solar heat managed to penetrate through that protective barrier and began violently boiling off volatile ices from deep inside the comet's interior, materials that hadn't seen sunlight since the comet first formed in its distant home system. The real comet, the blue, violently outgassing chemical engine hidden beneath that protective crust, only truly revealed itself to our instruments when it finally approached close enough to the sun for that outer layer to be completely stripped away or burned through. This revelation suggested that what we had been observing for months was essentially just the outer shell of 3I, Atlas, and we were only now beginning to see its true composition and nature. But these solar observation probes operating in Earth's orbital vicinity weren't the only spacecraft watching this cosmic drama unfold with great interest. Just before its perihelion passage and closest approach to the Sun, 3I, Atlas paid an unexpected visit to our small red neighboring world, passing at a distance of merely 0.19 astronomical units, which translates to approximately 28 million kilometers from the planet Mars. This represented an extraordinary stroke of cosmic luck, a rare and valuable opportunity for the impressive fleet of robotic explorers currently conducting scientific investigations on and around the red planet to observe an interstellar object at relatively close range. NASA's Mars Reconnaissance Orbiter, commonly abbreviated as MRO, swiveled its powerful high-rise camera, the High-Resolution Imaging Science Experiment, to point directly toward this unusual visitor passing through Martian skies. Now, to appreciate just how remarkable an opportunity this represented, you need to understand the capabilities of the high-rise camera system. This instrument is sufficiently powerful and sophisticated that it can resolve and image objects as small as a coffee table sitting on the Martian surface from its operational orbit 200 to 400 kilometers above the planet, providing resolution detailed enough to study individual boulders and small-scale geological features with unprecedented clarity. If any instrument humanity had positioned in space was going to successfully capture a resolved, detailed image of 3I, Atlas's solid nucleus, this camera represented our best chance. However, circumstances beyond NASA's control significantly complicated this observational opportunity. The U.S. government shutdown that occurred during this period affected many of NASA's operational departments and divisions, creating bureaucratic obstacles that meant it took several frustrating weeks before the captured images could be properly processed, peer-reviewed, and officially published for scientific and public consumption. The extended wait to finally get access to these eagerly anticipated images sparked numerous conspiracy theories across social media platforms and internet forums, with some individuals speculating that NASA had observed something highly unusual in the images, perhaps something suggesting extraterrestrial technology or artificial origin, and were deliberately withholding this shocking discovery from public knowledge to prevent panic or for national security reasons. The images that NASA finally released to the public nearly 6 weeks after they were originally captured turned out to be thoroughly underwhelming to those hoping for confirmation of alien technology. The photographs reveal merely a fuzzy, completely unresolved blob of brightness, essentially just a diffuse patch of light with no discernible structure or detail of the nucleus itself visible whatsoever. Even from this relatively close distance by solar system standards, the solid nucleus of 3I, Atlas, remained completely hidden and obscured, deep within an enormous shroud of gas and dust that measured approximately 1,500 kilometers across a cloud, so vast and opaque that it utterly defeated even HiRISE's remarkable imaging capabilities. Although scientists and space enthusiasts didn't receive the beautiful, pristine, high-resolution photograph of our interstellar visitor that many had been hoping for and anticipating, this apparent non-detection may paradoxically still prove scientifically valuable by helping researchers establish better constraints on exactly how large 3I, Atlas's solid nucleus, actually is beneath all that obscuring material. Fortunately, we don't have to rely solely on these inconclusive images from Mars Reconnaissance Orbiter to estimate the comet's size. Previous observations conducted by the venerable Hubble Space Telescope, utilizing its advanced imaging capabilities to study 3I, Atlas from Earth orbit before the comet disappeared behind the Sun, have already established with reasonable confidence that the solid nucleus is likely no more than 2.8 kilometers in width at its widest point, making it a relatively modest-sized object compared to some of the larger comets that inhabit our own solar system, though still substantial enough to generate the tremendous displays of activity we've been observing. But Mars Reconnaissance Orbiter wasn't operating alone in this observational campaign. The European Space Agency was simultaneously busy imaging 3I, Atlas using 2 of their Martian spacecraft, Mars Express, which has been faithfully orbiting the red planet since 2003, and the ExoMars Trace Gas Orbiter, a more recent arrival designed to study the Martian atmosphere in unprecedented detail. Meanwhile, NASA's MAVEN orbiter, the Mars Atmosphere and Volatile Evolution spacecraft, deployed its sophisticated ultraviolet spectrograph instrument to image the comet's extensive hydrogen envelope, successfully revealing a truly massive cloud of hydrogen gas extending far beyond the visible boundaries of the coma that could be observed in regular photographs. Perhaps most incredibly and unexpectedly of all, the Perseverance rover, currently sitting in Jezero crater on the Martian surface, fresh from its groundbreaking discoveries of what might represent evidence of ancient microbial life preserved in Martian rocks, actually pointed its Mastcam-Z camera system skyward toward the heavens above Mars. In the resulting long-exposure images captured by this surface-based perspective, photographs requiring extended exposure times to gather sufficient light from the distant Comet 3I, Atlas appears as a faint, ethereal, almost ghostly smudge drifting slowly among the background field of stars. These particular images may not appear particularly impressive or dramatic to casual observers expecting spectacular cosmic vistas, but their scientific and historical significance cannot be overstated. This represents the very first time in human history that we have ever successfully imaged an interstellar object, something that originated beyond our solar system, from the surface of another world beyond Earth. It's a genuinely historic milestone that speaks to both our technological capabilities and our expanding presence throughout the solar system. And then finally arrived the moment that astronomers, planetary scientists, and space enthusiasts around the globe had been anxiously awaiting for months. Perihelion, that point of absolute closest approach to the Sun when the comet would experience maximum heating and maximum activity. As 3I, Atlas emerged from behind the Sun's overwhelming glare in November, finally becoming visible once again to Earth-based observatories after its month-long disappearance. Something unexpected occurred. Panic and alarm spread rapidly through the astronomical community as preliminary observations suggested something might have gone catastrophically wrong. Harvard astrophysicist and enthusiastic 3I Atlas commentator Professor Avi Loeb, a well-known figure in the field who has previously made controversial suggestions about potential artificial origins for Oumuamua, publicly suggested, based on initial observations, that the comet appeared to have fragmented into multiple pieces, that it had essentially exploded, or broken apart, into approximately 16 separate fragments. The implications were deeply concerning. If true, it would mean that our precious opportunity to study this rare interstellar visitor in detail might be effectively over for good, with the nucleus destroyed and the comet reduced to a dispersing cloud of debris. Loeb's fragmentation hypothesis was primarily fueled by theoretical calculations, suggesting that the rate of mass loss 3I Atlas had been exhibiting during its close solar approach was fundamentally unsustainable for any cohesive object. With the brightness surging so intensely and so dramatically far exceeding normal cometary behavior, some computational models and theoretical frameworks predicted that the nucleus simply must have catastrophically disintegrated to provide sufficient surface area for the enormous amount of sublimation activity being observed. The math seemed to suggest the comet was releasing more material than could reasonably come from an intact nucleus of the estimated size. However, subsequent detailed observations conducted by astronomers at the Lowell Observatory and the Virtual Telescope Project, utilizing more sensitive instruments and more favorable viewing conditions as the comet moved farther from the Sun's glare, have substantially calmed these initial fears and concerns. Dr. Qicheng Zhang reported after careful analysis of the new data that the comet appears perfectly normal and healthy by all observable measures, certainly far more intact than the fragmentation hypothesis would predict. High-resolution imaging revealed no train of separate fragments trailing behind the main body, no chaotic expanding debris cloud indicative of catastrophic structural failure, no evidence whatsoever of the disintegration that initial observations had suggested might have occurred. The nucleus had survived its hellish journey through perihelion completely intact, The apparent explosion that had sparked such concern was revealed to be simply an extraordinarily intense but ultimately normal period of cometary activity, a natural firework display driven by the violent shedding of that ancient outer crust we discussed earlier, exposing fresh, volatile, rich material to direct sunlight for the first time in eons. So the comet remains in one coherent piece, its nucleus intact despite the tremendous stresses it endured. But those who have been closely following the unfolding story of 3I Atlas over the last several months of intense observation and analysis will likely not be particularly surprised to learn exactly why Professor Avi Loeb was so specifically concerned that it might have fragmented rather than survive perihelion intact. Over the past few months, Loeb has published an extensive series of detailed articles on the Medium platform, vigorously arguing that 3I, Atlas's observed behavior, exhibits what he characterizes as anomalies, deviations from expected cometary behavior that he suggests might be consistent with extraterrestrial technology rather than natural processes. It's important to understand that Loeb has developed something of a reputation in recent years for proposing artificial or technological explanations for unusual astronomical observations, particularly regarding interstellar objects, and his views on this topic have generated substantial controversy within the scientific community, specifically regarding 3I Atlas. Loeb has focused his attention on two primary features that he argues cannot be easily explained by conventional cometary physics. First, what he describes as a sunward jet, visible in various images, an apparent stream of material being ejected toward the sun, rather than away from it as we typically expect for comet tails. And second, what he characterizes as evidence of non-gravitational acceleration that maintains the object on what appears to be a remarkably straight trajectory through the solar system, rather than following a purely gravitational path. Loeb's argument regarding mass loss runs as follows. He calculates that the amount of mass loss that would be required to produce the observed magnitude of acceleration through the rocket effect of outgassing would be absolutely immense, potentially sufficient to completely disintegrate an object of 3I, Atlas's estimated size over the course of its solar system passage. He suggests that if careful analysis reveals that the observed gas cloud surrounding the comet isn't massive enough or dense enough to account for the observed thrust and trajectory modifications through natural outgassing alone, then we must seriously consider alternative explanations, specifically the possibility of some form of artificial propulsion system deliberately controlling the object's path. As intellectually stimulating and exciting as this hypothesis is to contemplate, and as much as many of us might secretly hope it turns out to be true because of the profound implications it would carry for our understanding of our place in the universe, in this particular case, unfortunately, the weight of evidence strongly suggests that standard, well-established cometary science offers robust and entirely satisfactory natural explanations for all of these supposedly anomalous phenomena that Loeb has highlighted. Let's address the sunward jet first, as this is perhaps the most visually striking feature that has captured public attention. Normally, based on our understanding of how solar radiation pressure works, we expect comets to display tails, trails of gas and dust particles expelled from the comet's surface that are pushed behind the comet by the solar wind, always pointing away from the sun regardless of the comet's direction of motion through space. This creates the classic appearance of a comet with its tail streaming behind it like cosmic hair flowing in a breeze. However, 3I Atlas has been observed to also possess what appears to be a second tail, extending in the opposite direction, apparently facing toward the sun instead of away from it, which certainly seems counterintuitive at first glance. Images captured by the 2-meter twin telescope, abbreviated as TTT, at the prestigious Teide Observatory, located in Spain's Canary Islands, and taken on the 2nd of August, but only first publicly released in October, show this unusual jet feature in remarkable close-up detail. This particular composite image, constructed by combining and stacking 159 separate exposures, each lasting 50 seconds, a technique that dramatically improves signal-to-noise ratio and reveals faint details, shows 3I Atlas appearing as a prominent black dot positioned at the center of a bright white glowing halo. But if you examine the image carefully, you'll notice that this glowing ring isn't uniform. There's a distinct break in the circular symmetry that reveals a jet of material blasting off from the comet's nucleus in the direction pointing toward the Sunday. Now, while this feature might initially appear to resemble a thruster or rocket engine firing against the direction of motion, exactly the kind of thing you might expect from artificial propulsion, this sunward jet phenomenon is actually a reasonably common and well-documented feature, observed in arcing numerous natural comets throughout the history of cometary astronomy. The physics behind its formation are well understood and thoroughly consistent with natural processes requiring no exotic explanations. As any comet approaches the Sun and begins experiencing significant solar heating for the first time, the side of the comet's nucleus facing directly toward the Sun will naturally heat up much faster and reach much higher temperatures than the portions in shadow or facing away from the solar radiation. If there happens to be a weak spot or fracture in the surface crust at a location facing sunward, perhaps a thin area of the protective mantle, or a region where ice extends closer to the surface, sublimating gases, building up pressure beneath that weakened area, can violently burst through and shoot outward from the comet in a jet aimed directly toward the Sunday. The solar wind, that continuous stream of charged particles flowing outward from the Sun in all directions, then acts upon this ejected material, pushing it back and deflecting it, creating a fan-shaped or spiral structure that, when viewed from Earth's particular perspective and geometry relative to the comet's position, can appear to form what looks like a forward-facing spike or tail. This is purely an effect of viewing geometry and natural gas dynamics, not evidence of artificial propulsion. This is genuinely not an unusual or unprecedented phenomenon to observe in cometary studies. In fact, very similar sunward-facing features and jets have been extensively documented and studied on numerous other comets, including the famous Comet Halley during its 1986 apparition, the spectacular Comet Neowise that graced our skies in 2020, and Comet 67P Churyumov-Gerasimenko, which the European Space Agency's Rosetta spacecraft studied in intimate detail for over 2 years, capturing thousands of images showing active jets erupting from various locations on its surface, including sunward-facing ones. Second, let's carefully address the supposed evidence of non-gravitational acceleration that Loeb has emphasized in his arguments. What we're actually discussing here is what planetary scientists call the rocket effect, a well-understood phenomenon caused by asymmetric outgassing from a rotating cometary nucleus, and this represents absolutely standard, expected behavior for all significantly active comets, not anomalous behavior requiring exotic explanations. When volatile materials sublimate from a comet's surface and blast off into space, they carry momentum with them, and by Newton's third law of motion, this imparts an equal and opposite momentum to the nucleus itself, creating a small but measurable thrust. If this outgassing occurs asymmetrically, for instance, if one hemisphere of the rotating nucleus is more active than the other, or if jets preferentially fire in certain directions, this creates a net thrust that can subtly alter the comet's trajectory in ways that purely gravitational calculations wouldn't predict. This is completely normal cometary physics that has been observed and measured in countless comets. A new comprehensive dynamical study conducted by researchers Goldie Ahuja and Shashikaran Ganesh has meticulously modeled 3I, Atlas's trajectory and orbital evolution backward through time over the last 100 years, carefully accounting for gravitational perturbations from all the major planets. Their detailed analysis found that the magnitude and direction of the comet's observed non-gravitational acceleration is entirely consistent with, and in fact precisely matches predictions based on the fire hose rate of water loss that Swift Observatory measured, and the massive carbon dioxide release that we've observed through spectroscopic analysis. The comet is indeed losing mass rapidly through violent outgassing, exactly as Loeb's calculations correctly indicate it would need to be doing to produce the observed accelerations. However, the fact that the nucleus has demonstrably survived this mass loss intact and appears structurally sound rather than disintegrating suggests that the object possesses sufficient density, structural integrity, and internal cohesion to withstand these stresses. Not that it must be artificial in nature to explain its survival. Natural cometary nuclei, particularly those that may have been compressed and strengthened by billions of years in interstellar space, can be surprisingly robust objects. Furthermore, the supposedly straight-line trajectory that Loeb has highlighted as unusual is largely a matter of observational perspective and choice of reference frames rather than any genuinely anomalous behavior. When an object follows a hyperbolic orbit, meaning it's traveling fast enough to escape the sun's gravitational pull entirely rather than being captured into a bound elliptical orbit, it travels with such high velocity that sun's gravity bends its path proportionally less than it would for a slower-moving captured object. This makes hyperbolic trajectories appear relatively straighter when plotted, but the object is still absolutely and precisely following the predictable mathematical laws first described by Johannes Kepler and Isaac Newton centuries ago. There's nothing mysterious about this whatsoever. While Professor Loeb's hypotheses and willingness to consider unconventional explanations certainly serve a valuable purpose within the scientific community by pushing us to rigorously question our assumptions and avoid overlooking genuinely anomalous phenomena due to theoretical biases, the current overwhelming weight of observational evidence, including the detailed chemical identification of cyanide compounds, substantial quantities of water vapor, and that massive carbon dioxide component we'll discuss further, strongly supports the conclusion that 3I Atlas is fundamentally a natural object formed by ordinary astrophysical processes, not an artificial construct. And now, the Meerkat radio telescope array in South Africa has provided what many scientists consider effectively conclusive evidence that has essentially ended this debate about artificial versus natural origins. Meerkat, one of the world's most sensitive radio astronomy facilities, successfully detected a faint but unmistakably distinct signal emanating from 3I Atlas at the precise frequencies of 1,665 and 1,667 MHz. These specific frequencies are instantly recognizable to radio astronomers as the characteristic absorption lines produced by hydroxyl radicals, those same OH fragments we discussed earlier in connection with the Swift Observatory ultraviolet observations. We mentioned hydroxyl radicals previously when discussing Swift's measurements, but this new radio detection from Meerkat carries crucially different and more definitive scientific implications. While ultraviolet observations can be scattered and absorbed by dust, limiting what depths of the coma we can probe, radio waves possess the remarkable ability to penetrate even the thickest, most opaque dust clouds without significant attenuation, giving us an unobstructed direct look at the gas density and composition within regions that would be completely invisible at other wavelengths. The successful detection of these hydroxyl emission lines at radio frequencies definitively confirms the presence of substantial quantities of water vapor, and lots of it being actively produced within 3I Atlas's coma through the breakdown of water molecules by solar radiation. This represents a genuinely historic first. This is the very first time in the history of astronomy that we have successfully detected radio frequency emissions from a confirmed interstellar object. No previous interstellar visitor, including Oumuamua or 2I Borisov, was ever detected at radio wavelengths. This radio detection conclusively confirms that 3I Atlas is chemically similar to essentially indistinguishable in its fundamental composition from the natural comets that populate our own solar system. It is demonstrably a wet, ice-rich body, actively venting copious water vapor as it heats up under solar radiation. If 3I Atlas were instead a dry, rocky object, or if it were some kind of defunct technological probe or spacecraft constructed from metals and synthetic materials, as some speculation has suggested, this characteristic hydroxyl radio signal simply would not exist. The chemistry is incompatible with artificial materials. This detection effectively seals the case decisively. 3I Atlas is fundamentally composed of water, ice, and carbon compounds, the basic building blocks of natural planetary systems throughout the universe, not some exotic extraterrestrial alloy or technological construction. So much for the alien spaceship hypothesis and technological origin speculations. This object is undeniably, unambiguously, conclusively, a comet formed by natural processes, but that definitive classification doesn't mean it's not continuing to surprise us in other fascinating and scientifically valuable ways that are rewriting our understanding of interstellar objects. One of the most fundamental assumptions that scientists have traditionally made about interstellar objects like 3I Atlas is that they should be essentially pristine, perfectly preserved time capsules completely unchanged. Since their formation, we've tended to imagine them as cosmic fossils, still bearing the exact chemical signatures and physical properties they possessed at the birth of their parent star systems billions of years ago, frozen in time by the extreme cold and isolation of interstellar space where no processes existed to alter them. But a groundbreaking new paper authored by Dr. Romain Maggiolo from the prestigious Royal Belgian Institute for Space Aeronomy, along with his international team of colleagues, fundamentally challenges and overturns this assumption entirely. Their research suggests that we have been conceptualizing and thinking about interstellar objects completely wrong from the beginning. 3. I, Atlas. They compellingly argue, based on detailed chemical analysis, is not pristine at all. It has been thoroughly cooked by its billions of years wandering through interstellar radiation fields. The evidence supporting this radical reinterpretation comes from detailed chemical composition data revealed by spectroscopic observations conducted by the James Webb Space Telescope, humanity's most powerful infrared observatory, the SPHERICS mission, which together detected an absolutely extreme and unprecedented abundance of carbon dioxide within 3 I Atlas's coma, far exceeding anything observed in solar system comets. In typical comets originating from our own solar system's Kuiper belt or Oort cloud, water ice overwhelmingly represents the primary volatile component and the main driver of observable cometary activity. As the comet approaches the sunday, you characteristically observe large quantities of water, vapor, and only modest, relatively small amounts of carbon dioxide gas. The typical ratio of carbon dioxide to water, measured in normal solar system comets, averages around 0.12, meaning roughly 12% as much CO2 as H2O by molecular abundance. In stark and shocking contrast, careful measurements of 3I Atlas reveal a CO2 to water ratio of approximately 7.6, more than 60 times higher than the normal solar system baseline value. Think carefully about the implications of that staggering figure for a moment. This comet contains nearly 60 times more carbon dioxide relative to water than standard cometary models would ever predict. It's behaving less like a typical dirty snowball and more like what planetary scientists might describe as a dry ice bomb with an ice shell. Where could this extraordinary excess of carbon dioxide possibly have originated? How do you produce such bizarre, anomalous chemistry? Dr. Maggiolo's team proposes a fascinating and elegant mechanism to explain this. Prolonged exposure to galactic cosmic rays, commonly abbreviated as GCRs, those high-energy charged particles that constantly permeate interstellar space. For the billions of years that 3I Atlas has spent drifting in isolation through the vast emptiness between star systems, traveling through the interstellar medium on its long journey from its distant birthplace to our solar system, it has been continuously and relentlessly bombarded by these high-energy particles originating from distant supernovae explosions and the intensely energetic environments surrounding active galactic nuclei. These cosmic ray particles, traveling at significant fractions of the speed of light, slam violently into the comet's exposed surface with tremendous energy, penetrating meters deep into the ice, rather than being stopped at the surface. When these high-energy particles collide with molecules in the ice, they deposit their kinetic energy by breaking chemical bonds, knocking atoms out of their molecular structures, and creating highly reactive chemical fragments that can then recombine in new configurations. The computational model developed by Maggiolo's team suggests that over timescales of billions of years, the likely age of 3I Atlas, based on its trajectory and velocity, this constant radiation bombardment gradually converts simple molecules, like carbon monoxide and water ice, into more complex and stable molecules, including carbon dioxide and complex organic solid materials. This process effectively creates what the researchers describe as a processed crust, or radiation-modified outer layer, essentially a thick shell of radiation-burned chemical products fundamentally different in composition from the pristine interior that extends approximately 15 to 20 meters deep into the comet structure. This is not a thin surface coating. This represents a substantial fraction of the radius of an object, only 2.8 kilometers across. Because 3I Atlas is relatively small compared to many comets, and because it's currently eroding and losing mass extraordinarily rapidly through the violent outgassing we've been observing, what our telescopes and spectrographs are detecting and measuring right now isn't actually the deep, primordial, unaltered interior composition of the comet that would tell us about conditions in its birth system. Instead, we're primarily observing this radiation-processed cooked outer crust, sublimating away and revealing its altered chemistry. In a very real sense, 3I, Atlas has caught the cosmic equivalent of an extreme suntan during its billions of years of exposure, and now it's dramatically peeling under the sun's intense heat. This finding carries profound implications for how we should interpret observations of any interstellar object. It implies that essentially any object that has spent geological timescales hundreds of millions to billions of years wandering through the radiation-permeated void of interstellar space will inevitably develop similar radiation-processed surface layers and will exhibit chemical anomalies compared to native solar system objects that have been shielded within our sun's protective heliosphere. We may quite possibly never observe a truly pristine, chemically unaltered interstellar object until we manage to catch one that is incredibly young, having been ejected from its parent system only recently on cosmic timescales, or until one fragments completely to expose its unaltered core material to our instruments. This realization fundamentally changes how we need to approach the study of interstellar visitors. But the elevated carbon dioxide content isn't the only chemical surprise that 3I Atlas has been concealing within its ancient ice. Dr. Josep Trigo Rodriguez and his team of colleagues conducted a detailed comparative analysis, carefully matching the reflected light spectrum of 3I Atlas against the known spectroscopic signatures of various meteorite types that have been collected and extensively studied on Earth. What they discovered was genuinely staggering and completely unexpected. 3I Atlas's spectrum appears remarkably similar to that of extremely rare CR-type carbonaceous chondrite meteorites, primitive, carbon-rich meteorites that contain tiny embedded grains of metallic iron and nickel that somehow survived from before our solar system even formed. This spectroscopic similarity strongly suggests that 3I Atlas may well be carrying significant quantities of these metal particles distributed throughout its icy matrix iron and nickel grains, mixed in with the water, ice, and carbon compounds. The presence of metals within what appears to be a comet is highly unusual and wasn't something scientists anticipated finding. In fact, spectroscopic observations conducted by the UVS instrument, the ultraviolet and visual Echelle spectrograph at the Very Large Telescope facility in Chile, successfully detected the spectroscopic signatures of gaseous nickel and iron atoms within 3I Atlas's coma as far back as September, with their data revealing that the comet possesses an unusually high nickel-to-iron ratio compared to typical solar system materials. This discovery was genuinely unexpected and has no clear parallel among comets originating within our own solar system, not even 2I Borisov, that other interstellar visitor we observed back in 2019, showed such characteristics. The VLT observing team noted something else particularly interesting in their data. The measured nickel-to-iron ratio appeared to gradually decrease as 3I Atlas continued approaching the sun and experiencing higher temperatures, suggesting perhaps that different volatile metal compounds were being preferentially released at different temperature regimes. The team noted that Comet 3I could soon become indistinguishable from solar system comets in this respect, as the ratio normalized. Why would the presence of metallic grains embedded within 3I Atlas matter so much scientifically? What makes this detection so significant beyond mere curiosity? The answer lies in some fascinating chemistry that could potentially explain many of the comet's most dramatic behaviors. When water ice melts or transitions to liquid within the comet's porous, fractured, crustal material, perhaps heated by direct solar radiation penetrating through cracks, or possibly by internal pressure and friction, as gases try to escape this liquid water, inevitably comes into direct contact with these embedded metal particles scattered throughout the structure.